The Foundations of Geometry by David Hilbert.
Chapter 7. Geometrical Constructions Based upon the Axioms of Groups 1 through 5. Section 38. The Representation of Algebraic Numbers and of Integral Rational Functions as Sums of Squares. The question of the possibility of geometrical constructions by the aid of a straight edge and a transfer of segments necessitates, for its complete treatment, particular theorems of an arithmetical and algebraic character, which, it appears to me, are themselves of interest. Since the time of Fermat, it has been known that every positive integral rational number can be represented as the sum of four squares. This theorem of Fermat permits the following remarkable generalization. Definition: let K be an arbitrary number field, and let M be its degree. We will denote by K prime, K double prime, ... through K M minus 1, the M minus 1 number fields conjugate to K. If among the M fields, K, K prime, K double prime through K M minus 1, there is one or more formed entirely of real numbers, then we call these fields real. Suppose that the fields K, K prime through K S minus 1 are such. A number alpha of the field K is called in this case totally positive in K, whenever the S numbers conjugate to alpha contained respectively in K, K prime, K double prime through K S minus 1 are all positive. However, if in each of the M fields K, K prime, K double prime through K M minus 1, there are also imaginary numbers present, we call every number alpha in K totally positive. We have then the following proposition. Theorem 42. Every totally positive number in K may be represented as the sum of four squares, whose bases are integral or fractional numbers of the field K. The demonstration of this theorem presents serious difficulty. It depends essentially upon the theory of relatively quadratic number fields, which I have recently developed in several papers. We will here call attention only to that proposition in this theory which gives the condition that a ternary diophantine equation of the form alpha chi squared plus beta eta squared plus gamma zeta squared equals 0 can be solved when the coefficients alpha, beta, and gamma are given numbers in K, and chi, eta, zeta are the required numbers in K. The demonstration of Theorem 42 is accomplished by the repeated application of the proposition just mentioned. From Theorem 42 follows a series of propositions concerning the representation of such rational functions of a variable with rational coefficients as never have negative values. I will mention only the following theorem, which will be of service in the following sections. Theorem 43. Let f of x be an integral rational function of x whose coefficients are rational numbers and which never become negative for any real value of x. Then f of x can always be represented as the quotient of two sums of squares of which the bases are all integral rational functions of x with rational coefficients. Proof. We will denote the degree of the function f of x by m, which in any case must evidently be even. When m is equal to 0, that is to say, when f of x is a rational number, the validity of Theorem 43 follows immediately from Fermat's theorem concerning the representation of a positive number as the sum of four squares. We will assume that the proposition is already established for functions of degree 2, 4, 6 through m minus 2. And show in the following manner its validity for the case of a function of the mth degree. Let us first of all consider briefly the case where f of x breaks up into the product of two or more integral functions of x with rational coefficients. Suppose p of x to be one of those functions contained in f of x, which itself cannot be further decomposed into a product of integral functions having rational coefficients. It then follows at once from the definite character which we have given to the function f of x that the factor p of x must either appear in f of x to an even degree or p of x must be itself definite. That is to say, must be a function which never has negative values for any real value of x. In the first case, the quotient f of x divided by the quantity p of x squared, and in the second case, both p of x and f of x divided by p of x are definite, and these functions have an even degree less than m. Hence, according to our hypothesis, in the first case, f of x divided by the quantity p of x squared, and in the last case, p of x and f of x divided by p of x may be represented as the quotient of the sum of squares of the character mentioned in Theorem 43. Consequently, in both of these cases, the function f of x admits the required representation. Let us now consider the case where f of x cannot be broken up into the product of two integral functions having rational coefficients. The equation f of theta equals 0 defines, then, a field of algebraic numbers, k of theta, of the nth degree, which, together with all their conjugate fields, are imaginary. Since, according to the definition given just before the statement of Theorem 42, each number given in k of theta, and hence also -1, is totally positive in k of theta. It follows from Theorem 42 that the number -1 can be represented as the sum of the squares of four definite numbers in k of theta. Let, for example, -1 be equal to alpha squared plus beta squared plus gamma squared plus delta squared, where alpha, beta, gamma, and delta are integral or fractional numbers in k of theta. Let us put alpha equal to a sub 1 times theta to the m minus 1 plus a sub 2 times theta to the m minus 2 plus ... plus a sub m equal to phi of theta. Beta equal to b sub 1 times theta to the m minus 1 plus b sub 2 times theta to the m minus 2 plus ... plus b sub m equal to psi of theta. Gamma equal to c sub 1 times theta to the m minus 1 plus c sub 2 times theta to the m minus 2 plus ... plus c sub m equal to chi of theta. And theta equal to d sub 1 times theta to the m minus 1 plus d sub 2 times theta to the m minus 2 plus ... plus d sub m equal to rho of theta, where a sub 1, a sub 2, ... a sub m, ... through d sub 1, d sub 2, ... through d sub m are the rational numerical coefficients, and phi of theta, psi of theta, chi of theta, and rho of theta, the integral rational functions in question, having the degree m minus 1 in theta. From equation 1, we have 1 plus the quantity phi of theta squared plus the quantity psi of theta squared plus the quantity chi of theta squared plus the quantity rho of theta squared is equal to 0. Because of the irreducibility of the equations f of x equals 0, the expression f of x equals to 1 plus the quantity phi of theta squared plus psi of theta squared plus chi of theta squared plus rho of theta squared represents necessarily an integral rational function of x which is divisible by f of x. F of x is then a definite function of the degree 2m minus 2 or lower. Hence the quotient capital F of x divided by small f of x is a definite function of the degree m minus 2 or lower in x, having rational coefficients. Consequently, by the hypothesis we made, capital F of x divided by small f of x can be represented as the quotient of two sums of squares of the kind mentioned in Theorem 43, and since f of x is such a sum of squares, it follows that f of x must also be a quotient of two sums of squares of the required kind. The validity of Theorem 43 is accordingly established. It would be perhaps difficult to formulate and demonstrate the corresponding proposition for integral functions of two or more variables. However, I will here merely remark that I have demonstrated in an entirely different manner the possibility of representing any definite integral rational function of two variables as the quotient of sums of squares of integral functions, upon the hypothesis that the functions represented may have as coefficients not only rational but any real numbers.
The Foundations of Geometry by David Hilbert. The material contained in the following translation was given in substance by Professor Hilbert as a course of lectures on Euclidean geometry at the University of Göttingen during the winter semester of 1898 and 1899. It was translated by E. J. Townsend, Ph.D., University of Illinois. The text was downloaded from Project Gutenberg with the following notice: this ebook is for the use of anyone, anywhere in the United States and most other parts of the world at no cost and with almost no restrictions whatsoever. Read by Jim Renholt. Programming and illustrations by Jim Renholt. 2019. Portrait of David Hilbert by Rita Ray Renholt. Thank you for listening.